Welcome back to the lectures on GPU architectures and programming. So, in the last set of lectures, we were discussing the way the standard reductions can be optimized with respect to GPU based parallelization. Now, we will go into some more algorithmic examples. To be more specific, we will be talking about two examples. One is a Bitonic sort and the other is computation of a prefix sum. So, let's get started with this. So, when we are talking about Bitonic sort, the basic problem of sorting is you are given as input any random permutation of numbers, and you want to output a sorted set which is either ascending or descending in with respect to their respective keys of the. So, as we know that there are a lot of well-known comparison based sorting algorithms. So, in this case we will be choosing some algorithm which is very well known for the amount of parallelization that it offers. And so, before going into this the idea of what basically is Bitonic sort, we let's start with an introduction of sorting networks, and because that's a key idea which will be used in the context of Bitonic sorts. So, first of all, what's a sorting network? So, essentially it's a computational model, I would say, a network which is doing a sort which is essentially being used for performing the function of sorting. We are assuming that, so for example, consider that you have some wires. The wires are running from left to right and they are carrying values. So, each wire is carrying some physical signal value. Let's say some numerical value in terms of bits, like that. Consider an abstraction here. Now, the values are traversing through the network from the left to the right, and in between we have some comparator circuits connected to the wires, right. So, whenever I have a value coming in one input of the comparator circuit through one wire and another value coming through another input of the comparator circuit through another wire, the circuit will make a comparison, and depending on whether I want the max or the mean, it will if I want that the maximum value should flow up or the maximum value should flow down, accordingly the comparator will work and show up the values across the wires. So, that's the basic functionality here. Let's take an example. So, what we mean by this comparator operation, so these are my wires running from left to right. They are being provided with these inputs A and B, and this notation, this symbol down, this arrow pointing downwards, it's essentially telling me what I want is whatever is the input here, the comparator circuit is going to compare and find out what is the bigger value, and it will push the bigger value to the down wire and it will pop the smaller value to the upward wire. Okay. Now, of course, if A is anyway less than B, then nothing is going to change. If A is greater than B, then there will be a swap operation here. So, essentially the comparator ensures that whatever is the input, at this point I have the upper value to be less than the lower value, right. That is the invariant that is going to be ensured in the output lines here in this pair. Now, similarly, if we just reverse this arrow, that means we are looking for a comparator circuit which again compares A and B, the inputs, and in the output it is floating the maximum value in the upward wire and it is bringing the minimum value downward. So, essentially we are saying that, okay, we are trying to do a descending output here, and here we want a ascending output here. Okay. So, that's the primary goal of the comparator circuit. It's in this case, so you can just remember like this, the maximum value follows the arrow. That's the simple way to remember. The max value is always going to follow the arrow. In this case, it's going to percolate down. In this case, it's going to percolate up. So, here again in the output, the invariant that would be true is whatever is the value that I have in the wire here is always greater than the value that I have in the wire here. Fine. Now, what is the usefulness of these circuits and the sorting network we want to build? Now, consider a set of wires here. We have a more involved example. We are trying to build what we essentially mean by a sorting network here. So, essentially it's a collection of this kind of wires, and comparator circuits are placed like this. Okay. So, the important thing we need to understand here is the flow of time here. So, essentially we would mean that this is the input and this is the time following which, I mean, this is the flow of computation following the time axis, and here we are looking for the output. So now if you observe what's going on, suppose the input is already in ascending order. Sorry, the input is in this order, essentially it's a descending order, but we want the output to be in the ascending order, right? So since A is greater than B and B is greater than C, so on and so forth, in the output, D being the smallest element, if we want the output in ascending order, D should come followed by C, followed by B, and followed by A, and we can just do a small check that this sorting network can realize this functionality. So let's see what's happening. So we have given A and B as input. Now since A is greater than B, so A is going to flow down here, right? The max will follow the arrow. A comes here, B goes here. Similarly, C comes here, D goes here. Again, as we can see that A is definitely also greater than D by transitivity, and so B is also greater than D here, right? So D will go up, and naturally B will come down, and similar behavior we can take here. So what's going to happen is, after this, again we are now comparing A and C here. So again C will go up and A will go down, so on and so forth, right? Now what is important to point out here is, you can look at the set of comparisons that are going on with respect to time and try and understand what are the activities that can be done in parallel. So essentially, as long as I don't have a dependency between the inputs and outputs, those comparisons can easily be performed in parallel. For example, here this set of comparisons, I can easily do them in parallel, right? And can I do these two in parallel? Okay, why not? Because apparently there is no dependency between the inputs and outputs, right? Because here you are comparing A and D, and here you are comparing here you are comparing B and D, and here you are comparing A and C, right? So even this could have been done in parallel. Now what's happening is, so as the switchings of the values between the wires go on with respect to time, if we see the flow of values, the circuit is going to ensure that at the output I get the values in ascending order. I get D followed by C followed by B followed by A, right? So one thing we can now understand, it makes sense to think like this, that I can use this kind of a sorting network to represent the underlying algorithm of a sorting function, right? Any sorting algorithm. For example, bubble sort should have this kind of a sorting network representation, or insertion sort should have a separate, different, since it's a different algorithm, it should have its own sorting network representation, right? So for example, this, as we can see that this is a sorting network which is going to do a bubble sort. Well, we will not discuss any more here. We will provide the slides. You can just look into this and understand why we are saying this represents the bubble sort algorithm here. Of course, the generalization would be that any comparison based sort algorithm can be represented using this kind of a sorting network. So the way we have drawn the picture is to make you understand what are the operations we can actually do in parallel without any dependencies, and in that way bubble sort or any other sorting algorithm, as we can see, if we take a sorting network representation, it actually reveals to us what are the operations that are actually possible in parallel, right? That's the most important thing. So coming back to our idea here, we want to talk about Bitonic sort. So this algorithm has got two fundamental steps. The first step is that you convert any arbitrary sequence of numbers to a Bitonic sequence, right? Now what is a Bitonic sequence? It's a sequence of numbers which is first increasing strictly and then it's decreasing strictly. For example, this. So it's increasing up to AM, and then it's from AM to BN, it's strictly decreasing, right? So this is a Bitonic sequence, and so the first step of the Bitonic sort method is to consider as input any permutation of values or key value pairs and convert it into this kind of a sequence. And then the second step is, well, you take this kind of a Bitonic sequence as input and convert it into a sorted sequence. Just coming back once to this example, I hope from this it's clear to you that why we are trying to say that this is essentially a representation of bubble sort. As you can see that if I just follow the track of these downward arrows, the max val is kind of flowing down, right? The next max val will also similarly like flow down. The way we are drawing this picture is we are trying to show which are the operations that can be done in parallel, right? So maybe you can consider this kind of a picture and try and figure out why this represents a specific sorting algorithm, and you can also create sorting network representations of other sorting algorithms and figure out what is the parallelization that is possible for that algorithm, right? So coming back to this Bitonic sort idea, so as we can understand, the step 1 is to create the Bitonic sequence. The step 2 is to take as input the Bitonic sequence and then create a sorted sequence. The sort algorithm is actually going to implement these two steps in form of a, and we shall be trying to view those methods in the form of a sorting network, and then use the sorting network to identify what are the operations that can be done in parallel, similar to the previous examples of sorting algorithms. I will just repeat. So these are the two fundamental steps we are going to realize through a sorting network. So in step 1, we are going to implement a sorting network which can take as input an arbitrary sequence, convert the sequence to this kind of a sequence where it first increases and then it decreases, right? The sequence key value pairs decreases. And then we will have a stage 2 sorting network which will take this kind of a sequence as input, and it will provide a completely sorted sequence. So let's look into this for once. So let me just do a few corrections in this picture. Here I should have 8, and this should be 9 in the input. I hope the rest is correct here. Yeah. Okay. So we are trying to give here a sorting network using which we are performing the Bitonic sort, right? So we have these inputs 7, 8, 9, 11, 12, 3, 4, 2. As you can see, it's an arbitrary permutation, and we are trying to mark out the different steps here. So I have a step 1. That means, as per our previous definition here, step 1 is going to create a sequence here where the values will first increase and then the values are going to decrease, right? Now let's look at the network and see whether that's really happening or not. So in the first stage, again I will just repeat, this sorting network is trying to represent the operations with respect to time, right? That means at this time slot I can do these operations in parallel. In the next time slot I can do the following operations in parallel. In the next timestamp I can do the following operations in parallel. Now of course, in between operations happening at different timestamps, if there are no dependencies, then you can parallelize the operations across timestamps. We have to understand this, right? We'll give examples on that. So first point I am just repeatedly trying to make is, what is the sorting network trying to show you? It's trying to show you that this is the flow of time, and at each time instant what are the operations that I can do. Go to the next time instant, what are the operations I can do, and again I will just repeat, if there are operations sitting at different timestamps, but they really don't have any input output dependency, they can also be parallelized, right? So let's just first look at here the activities that are happening and try and figure out whether the functionality of the sorting algorithm is actually going to be realized through this sorting network. Well, first of all, as we can see, there will be no downward flow here, because 7 is always seven is of course less than 8, so the max is already here, nothing flows down. Here the max is below, so it will flow up. 11 goes up and 9 comes down. Similar thing here, and nothing changes here, right? Here what is happening? Again, I have to compare between 7 and 11, nothing changes. 8 and 9, nothing changes. But now 3 and so now here I have to compare 2 and 12, again nothing changes. And then I compare 2 with so here we are comparing 2 and this value 12, so that remains same. And then in this line we are comparing the value of 2 so here we are comparing 2 with the value of 4, that is done. And here we have 2 and 12, and once I compare them, again there is no change that's going to happen. And then again when I compare here, yes, so I will expect the maximum value to go up, and it's already up here as I can see. And just 1 minute, I think here, so the 4 is being here, and yet again yeah, so the issue is yeah, this is from where it will start. And so what I am going to get is, so I am comparing 2 and 12, nothing changes here, and yeah, now it's fine. So I am going to compare between 4 and 3. So the 4 is the max, it should go up following this. So 4 comes up and 3 goes down, right? So pardon the corrections here I have to do, extremely sorry for that. And now when I continue, so again I go to the next stage, nothing changes here, but here I have 11 which should come down, right, and 9 is going to come up. And similarly here 12 flows up, 4 flows down. And then again here nothing will change because 3 is the maximum and it's already here. So now let's observe the outputs here, because we are considering that step 2 finishes here, right? So what are the outputs? As we can see in the output, I have 7, 8, 9, 11 followed by 12, 4, 3, 2, right? So it's ascending and then it's descending, right? So it's ascending here and then it's descending here. So that means this is a Bitonic sequence, because if you go back to our previous definition, a Bitonic sequence is a sequence of numbers which will first strictly increase and then it will strictly decrease after that point, right? So that's what is happening here. Then we are going to the step 2, and in step 2 the definition is that, okay, I am expecting the input in the form of a Bitonic sequence, and I will transform it into either a fully ascending order output or a fully descending order output, right? So in this case we are trying to transform it to a fully ascending output, and let's see whether it is happening. Yes, it seems so. For example, I am going to compare now 7 and 12, they are already sorted, right? So then I compare 8 with 4, I exchange. Then I compare 9 with 3, nothing changes. Then I compare 11 with 2, and so it changes between 2 and 11. So that's done. And then in the next stage I compare 7 and 3, so again I have a change. I compare 4 and 2, again I have a change. And here I compare 12 and 9, I have a change. I compare 8 and 11, nothing changes. And then I am in the last change where I compare 3 and 2 with a switch, compare 7 and 4, again a switch, 8 and 9, again a switch, and 12 and 11, again a switch, right? But what I get in the output, as you can see, is fully sorted in ascending order, right? So apparently this Bitonic sort network that we have shown here does this job. Question is, will it do its job in general? Well, you can study a bit about this algorithm and look into its correctness proof, which is there in almost all of the algorithms books that are available. Because given the scope that we have here, let's assume that it works. But one fundamental thing we'll do, we'll look into the algorithm and try and understand why it works without going into proofs and other techniques for showing the correctness of the method. So, if we look into the intuition behind the algorithm, what is really happening? Observe something, that step 1 is using step 2 recursively on smaller sequences. Now, why is that so? Let us go back to the definition of a Bitonic sequence. So, it's first going to increase and then it's going to decrease, right? So, then I would say that smallest Bitonic sequence would be just a collection of two numbers, right? A collection of two numbers. And then if I apply my method of step 2, it's expecting as an input a Bitonic sequence, and it's going to provide as output the in a sorted order, ascending or a descending, right? So, essentially I can say that whatever is the method of step 2, it will take as input a Bitonic sequence and produce a fully sorted sequence, right? So, even for building the basic steps of step 1, I can apply step 2 recursively on the smaller sequences by starting with the smallest Bitonic sequences, which are of size 2, right? And in that case, for step 2, the only thing I will have is a single phase here, right? That okay, you are given the function Bitonic sort, which is expecting Bitonic sort step 2, which is expecting the input to be as a Bitonic sequence. So, I can just say that the way I am going to draw up the algorithm is, so consider step 2, give it as input just a smallest Bitonic sequence, 2 different values, and give the algorithm the order you want, right? That whether you want it to be an ascending order or you want it to be a descending order. What you get is output is one comparator, right? A smallest sorting network containing only one comparator, right? So, in that way I can keep on applying the step 2 recursively on smaller sequences from here and keep on constructing the different phases of step 1, right? So, in that way we need to remember that for constructing step 1, I can look into it as constructing subsequences by using smaller versions of step 2. If we look into this, what is happening here? Here step 2 is expecting an input which is a 8 size Bitonic sequence, right? If I look into the method here, just this subpart, right? If you look into this subpart, then I can say that, well, what is the input? At this input, I mean, if this is your input, 4 size input, here you have a Bitonic sequence as output, right? Because it's ascending and then it's descending, right? And then if you look into this part, you are essentially applying step 2 on an input of size 4. This is your step 2 on an input of size 8, here you are applying step 2 on an input of size 4, right. In that way, if you generalize, you can look into every part of step 1 and start saying that this is nothing but a smaller instance of step 2. So, this is the larger step 2, this is the smaller instance of step 2, and this is the even smaller instance of step 2, which is nothing but a single instance of a comparator, right. So, we will use this recursive formulation to generate the algorithm. First, let us look at a recursive C program which can perform the Bitonic sort by using the idea we just discussed. So, this is our basic comparator. It is considering two inputs I and j, and it is given a direction, right. Now, look at the way we are writing the program here. So, if the direction value is 1, ai is greater than aj, so, you are giving ai and aj as input and you are doing the comparison. If the direction is 1, if ai is greater than aj, then you are going to exchange, right. So, you are exchanging I and j. So, essentially in the output lines, what you are, if ai is greater than aj, then you do the exchange and you get effectively the value here this and the value here ai, right. So, what we get here is the bigger value is flowing down. So, this is the equivalent sorting network representation, because since ai is greater, you are doing the exchange, right. So, the bigger value is flowing down and this is the network that you have, right. So, this way this small comparator program represents this sorting network with a downward direction. Now, look at the merge step and let us understand why it works. Why do I say that the merge step is important? Because we understand that fundamentally we are going to use this recursive formulation, because we have understood the underlying recursive structure of the problem. If we are given a bigger, if we have to implement a Bitonic sort algorithm, what we will do is we take the whole input, divide it into two parts, right. This is our entire input, divide the input into two parts. For the first part, you apply the Bitonic sort algorithm with the direction ascending. So, the values will be increasing, right. So, the values increase, right. For the next part, you again apply the Bitonic sort algorithm with the direction reversed, right. So, the values would actually be decreasing downwards. So, here you have an ascending sequence followed by a descending sequence that gives you the Bitonic sequence. So, this is essentially your step 1, and then you have step 2, which is essentially the Bitonic merge, because already we have discussed it expects ascending followed by descending and is going to provide a fully ascending or descending output depending on what is the requirement, right. Now, we have also discussed that the step 1 is nothing but a generalization of step 2. I can keep on applying step 2 recursively on substructures to realize step 1, right, which means it's fundamental to understand the Bitonic merge problem, and all we need to do is we will be recursively calling the Bitonic sort on smaller instances, and finally the Bitonic merge function is the function which is going to do the job for us, because we have already identified, I am just repeating here, that step 2 or the merge is going to be the fundamental thing. Effectively that's doing the sorting for you on the smaller instances and just flowing it out on the larger values. So if we look into Bitonic merge in the general case, so you have given a low and a high, essentially the starting point and the ending point of values, and you have given the direction, right, and you are asking it to do the merge, right. So what's really going to happen? So now to better understand this, let's first look into the merged sorting network. As you can see, this is the merge step. The first thing we do is a sequence of comparisons. How many? Half of the size of the inputs, that is a number of comparisons we are doing. What is the stride of the comparison? Again, half of the size of the input. So at that size stride, I am doing 4 comparisons here, and that is essentially followed by what? Again a smaller instance of Bitonic merge here and a smaller instance of Bitonic merge here. Now this is important. Let's understand again the recursion present inside the Bitonic merge step. So this is really something we need to understand. First point is, we understood that step 2 is the most fundamental thing. Step 1 is nothing but a recursive application of step 2, because what's happening in step 2 is you are considering as input a Bitonic sequence, and then you are providing as output and the sorted sequence, right. And when we apply step 2 on smaller instances and combine them, that's essentially giving me step 1. So with this understanding, we will end this lecture and discuss the details of step 2 in the next lecture. Thank you.